Yes. I sent something class the other day, like just to my growth month. Do you plan anything for? Is that we have like a little something at the end of the semester? It's not a little. Yay! I have like no homework. I have. Right. I just probably go read. We looked through the literacy, adolescent literacy, not in the 4200.
Oh, you're the one.
There's your left-hand side. This side.
Yeah, I can see he's like not going to do anything. Yeah, like it should have been one procrastinator, one hard worker. Like that's how me and Katie were. She was like on it. This is what we're doing. This is what we do. I was like, okay. Right.
Like here I am still working on my text. I work on it. Good under pressure.
Okay. Like after this class, I'll probably.
Yeah, it's like the one time.
Like his
Between
stuff,
the street and.
Plus, like I'm sure have a kiddo.
Yeah, he's sick.
Oh.
Honestly, I was considering
Coming.
I think
Does he go to daycare or something?
It stays the same.
No.
So it just keeps saying.
Maybe they pick him up early or something. Maybe not really if you stay for the class, Is it hard being in school? Very, I bet.
2 kids for
Oh, for sure not. Yeah, I struggle with my.
if I'm home.
Is your husband?
this now.
He is for sure.
Oh, okay. So
Right?
no, active like in the military.
I'm sorry.
In the military.
Sorry, he is no longer.
Okay. Is he active? Like, yeah.
You mean like is he a
good father?
Yeah. You never know, right? No, he is. He's a reservist.
I would say this.
Really?
He did 4 years active.
Where would be 16?
Yeah. I know most people who do active really like it, especially
go
more
to
too.
the reserve.
Yeah. Yeah. Oh yeah. Yeah. My friend Peyton's in a nerdy.
No, I was just.
I think she wants to go active because she like doesn't really like she doesn't know what she wants to do with her life, but she's going to school to be a nurse, and she like hates it, like hates the classes and stuff. And she's kind of bored, but she's like, oh, I'm still. So she's like, I might just go active so I can just get out of here for a little bit. Airport, which is but what's he in?
He was in the
Oh, okay, so that's like the hardest. Yeah. That's cool.
I got all the way very much.
I'll show you where I got.
And then you got some squares or
Yeah.
Hold on.
Yeah.
And then you're gonna find out. Remember?
I got 3b squared equals a squared. And then I thought maybe b squared.
Keeping it single spaced and like
You can just
more, so I can be like, oh, I'm done.
It's on practice.
Forgot my math.
So then once you get to x squared,
Hey, good looking.
you know that x squared has to
Huh?
equal.
You guys looking? Are you going?
No, her husband is, and I'm not pregnant.
But a big part of the proof that everyone will position is that in cannot have common factors. Other
One of your sisters is active, right?
Yeah.
I can't hear what you say. I need to say.
I'll just put mechanism not excited because it's $4 copay.
That's hard.
I hate that, and I can't like
Row 2.
I can't hear it.
Like row 2.
Honey anymore.
Right? Let's go to
I just add like
Started like that.
yeah.
So why do you use k squared?
K squared.
On the homework. I didn't start it. Yeah.
I want to. That's what
Hey, we can have it come back. So since they don't come back, you're not going to
You slapped it.
look at it.
No.
I'm pretending I don't. I don't even know why I bought it.
That's so me too.
I didn't even open it.
For this class and my philosophy class. Yeah. You see, it's
I mean, there you go.
Yes.
She agreed on one.
Yeah.
That's where you do it.
It's all by hand.
Oh, right. So I did.
What did I do next time?
Okay, well, I'm taking stats next time.
That's like, that's good.
For 3.7?
That.
Is that 4 point? Oh.
I'm not sure about. That's all I know. I feel
So he made anything to do with she's a big application in that. He was like, that's not a good. Crazy. And I told her, I was like, why were you on? Amy. Like, you know that Mary? Amy?
Oh.
Whatever her name is. What's her name? Mary?
Very.
I'm gonna try to start writing meter on my homework.
Feels so bad. She told me, so it's like, I told her, like I called her Amy. It has not even the same letters.
You're almost there.
Almost there.
I'm gonna go somewhere. If I don't write down fast, the thought disappears.
Whatever.
Like
These versions.
oh, these content. He made mine very redo it. Is it at least 3 pages?
Yeah.
Okay, then you're good.
It's quite a few pages. But mine is.
I don't know what to add. I didn't
Yes.
read the actual book. He said, he's like, I wonder if it's in the book. Textbook. Oh, yeah, I know this song. You didn't tell us we were reading. You tell us on 8 other books.
Expectations. If you literally should have read.
Emily's.
Not gonna read.
I'm not reading. I just looked at the pictures. But Emily's is like one document, but it's 2.5 pages long and it's close to 33. So then I'm looking at this because it's like one poems.
Yes.
And then one document.
Yeah.
So I read. Yeah, I got that.
Forms. Right. These things, this, and it, like, I edited that you had in the attached bill. Like,
Yeah.
no, I couldn't really, like, nothing in this shows that I actually, like, I put in this yours.
Oh, okay.
That's not here.
Oh, so yours is only 2 pages.
Right, and then I have all of these.
Smart. That's what Jonas said he did too.
That's what I'm really good. This almost took a page and a half because
No, and the stitches and double spaced. You should have double spaced it.
Yeah. Yeah. I mean, if he wants to, I will double space it and I'll print it out if he really wants to, because that makes it clear.
Yeah.
I'm just going to keep it like this, because I already printed it, he was so intrigued anyway.
I
So.
know.
Also, when it says author, mine had like 7. So I picked the first 3, and I wrote them down.
And then write, what are you supposed to write when there's like extra, like E, F, et al, et al.
Yeah.
If there's like a whole bunch of them, you say like the first one and then et al. I like that.
And I feel like if you look at
So,
social studies, the United States, like J. Geiger, it would pull up. Yeah. I think that's all. But like,
so I'm just gonna delete this. Just delete this, like,
yeah, just do that. Just start writing yourself.
well, this is like an introduction.
Yeah.
That first one is.
So,
The examples like the overview.
Overview. Can't really, I didn't do this because I accidentally figured out that yesterday. And then, well, because I had to work at 6 a.m. this morning. By the time it was 11, I was like, I'm going to bed.
Even though I had to stay up because I had 6 assignments. People who calls me 7. I just pressed block. Where it said other, please.
I left
specify.
it.
I left it.
Oh, I put some.
I like wrote a couple of comments.
What did you say for the chapter parts? Mine doesn't
Long
have
time.
here.
Here's some
Content. That's what it
Nice.
Okay.
I was talking to Erin, I'm like, you always know when an education major comes from your business.
Oh, for sure.
I feel like you have so many different outfits and I wear the same like 4 hours. I just I probably should work this.
All right, let's get started. Make it.
Here.
Where?
Elsa.
Here.
Morgan.
Here.
Allison.
Here.
Katie.
Here.
Desi.
Here.
Thea.
Here.
Catherine.
Here.
Curtis.
Here.
Elsa and Katie, have you turned your homework 7 yet? Last
No,
week's
not
homework?
yet.
Not yet?
No.
Okay, so try to turn in your homework to Blackboard maybe today. As you do
Okay.
lose late, okay, lose points for turning in late. Okay. Well, I was going to go over the problems today, but I guess we have students who haven't turned in today, so I'm going to wait until next Monday to go over those homework problems. Because from the grading, I've seen a lot of, problems. So I think many students do have trouble writing proofs. So today we are going to continue chapter 4, method rejection. Okay, so far we have talked about 2 types of questions we can prove using mathematical induction. One of them is like the left side is adding a sequence of, I guess we can show you the homework. Adding a sequence of numbers is equal to a very easy formula, an easy algebraic expression or like a function. So, by adding those numbers, a list of numbers, it's very tedious to do that one by one. but with the formula, it can be very quick. So like the first 3 questions, which number 6 we did it last time. Looks like we most of them didn't have any trouble doing mathematical induction. The one I saw the problems would be the one in chapter 3. Those indirect proofs, so like number 15, number 16, and also I added a few questions, 2 questions there, number 28 and this one, number 3.7. Prove that if a squared is divisible by 3, then a is divisible by 3. That is the statement that you have to use in the proof of number 16c. So either you have to do it separately, or otherwise you have to prove that under 16c. Okay. So these are the ones with trouble. So it looks like the mathematical induction number 6 is actually most of you got it right. So the first type of question you could do is to use mathematical induction to prove this type of formulas. And last time, on Monday, we talked about the other type of question we could do by proving divisibility. For example, how do you prove 5 raised to n minus 1 is divisible by 4? Because by the definition, you will have to be able to factor a 4 out of here. Well, while we're looking at that, 5 to the n, we cannot factor out a 4. Minus 1, there's not a 4 there. Even if you do cases, it's not going to be able to work, because this minus 1, you can never, whatever you do to the cases of n, you're not going to be able to factor out a 4 from this minus 1 there. So the way we did it before, either the proof by cases or direct proof won't work anymore. So that's why we have to do, we can try mathematical induction. Number 6 is kind of similar to what we did before with 3 and 4. You just have to write down what will be the property if n equals 0. What will be the property if n equals k? What will be the property if n equals k plus 1? I did do an example last time, which was 2 to the n. 2 raised to 2n minus 1 is divisible by 3. It's very similar to this one here. So this is the one we did. We can go over this a little quick one more time. So what we do is, we write on the property, we'll say statement if n equals 1. In the homework, they ask you to start from 0. We actually can start from 0, but just if n starts from 0, in this case, actually for my case, you won't. It will work. Okay. So if n is 0, 2 to the 0 will be what? Any number raised to 0 is equal to what? 1, okay? Except 0 raised to 0. So 2 to if n equals 0, you get 2 to the 0 equals 1, and 1 minus 1. So 2 to the 2n minus 1. 2 to the 2n minus 1 is going to be equal to 1 minus 1, that is 0. And 0 is divisible by 0. By 3, sorry. 0 is divisible by 3, right? Can you all see that? Okay, why? Because you can factor a 3 out of 0. But you may see, well, there's not a 3 there, but because 0 is so special that you can factor any number out of 0. Because you can always write 3, a 0, you can write any number times 0. So that's, okay, even 0 is considered as an integer. So whenever you can write a number as 3 times the integer, then 3 divides that number. So 0 is divisible by any number. So that will still be true. Although when I did talk about this case, I started with n equal to 1. Even if I change this to 0, that should still work. So if n is 1, I got 2 to the second power minus 1 is 3, which is divisible by 3, which is also correct. Okay, so depending on which one basis case you're going to do, depending on what the question gave you, they always have to specify that. What is the smallest integer n will take? Okay, now inductive step is the difficult one. So let's see what we did. In the process, we used some algebra formulas. So we always assume the statement, it's not a formula anymore. And we assume the statement is true for n equal to k. So that means replace n with k. You got 2 to the 2k minus 1 is divisible by 3. And we're going to try to prove the statement is also true for n equal to k plus 1. So replace this n right here with k plus 1. So this is the one we want to prove. What if we change n to k plus 1? Will this still be divisible by 3? But what we know is, we know 2 to the 2k minus 1 is divisible by 3. But what if this k becomes a k plus 1? 2 to the 2k plus 1 minus 1, will that still be divisible by 3? That's what we need to do. And in order to do that, we, like I said, we use the algebra formula. First of all, we try to simplify this. So what we did over here is I added 1 to both sides. Oh, well, first of all, how did I get this equation right here? 2 to the 2k minus 1 equals 3n. Where does this come from? Can someone explain? Wait, can you repeat? Where does this come from? How did I get this equation? I substitute. Well, that first sentence assume 2 to the 2k minus 1 is divisible by 3. That is the substitution. I substitute k for n. But what about this equation? Where does this equation come from? So that first part right here, this sentence right here, statement, is a substitution. But what about the equation we got? How did I get that? What's the reason for that? I didn't put it there because I thought, at this point it should be very obvious now. What?
To show that it's divisible by 3, so 3 times an integer.
To show it is divisible by 3?
Or to prove that it is. So we assume that that's the equation because we want to prove that 2 to the 2n minus 1 is divisible by 3.
2 to 2n minus... Wait, this is not the one we want to prove. This is the one we assume it is true. So if you assume something is true, you don't have to prove it. Which one do we need to prove? It's when we replace this k with k plus 1. This is the one we need to prove. Right here. This is the one. Okay, look. It's k plus 1 there. That is the statement I want to prove. Okay, but this is the one, it's like assumption. We assume this is true, which means this is already true. You don't have to prove it. So in the inductive step, as you did in the homework, the inductive step, what do? We always prove this property, by calling it a property or a statement. We always prove if this is true for k, then this must be also true for k plus 1. So when you say this is true for k, if this is true for k, which means when you say the if part is the hypothesis, you already know 2 to the 2k minus 1 is divisible by 3. So you assume this to be true. But this is not the statement I want to prove. The statement I want to prove is when I replace this k with the k plus 1. That's the one I need to prove. Okay. So be clear about that. Now, again, go back to the question. Well, when I assume 2 to the 2k minus 1 is divisible by 3, remember, this is not the one we need to prove. This is like a given. This is known. This is something we already know. We know this is true, okay? But how did I get this equation? Well, I know 2 to the 2k minus 1 is divisible by 3, but where does this come from? This equation, where does it come from? Why is 2 to the 2k minus 1 equals 3 times an integer? By what? Everything you say, every conclusion you write down, it has to have a reason. It either follows from the definition or some property you have already proved before. Either you prove it in other homework assignments, or we prove it in class, or something you're going to prove. So where does this come from?
Divisible by 3?
Yes, that would be right. Okay, so if you remember, go back to the definition of divisibility. So if you say, you probably should add those to your notes. This was from Monday's class. You probably should put there, if you didn't remember where this comes from, it's by the definition of divisibility. Definition of, kind of outer space here. So by the definition of divisibility. So I'm going to go back to review that. What is the definition of divisibility? It's saying if A divides B, what will follow from that? If we know A divides B, then there exists an integer k such that B equals A plus A times k, right? Okay. So this k exists. That is the definition. That's how I got that. Because this number, whatever that number is, it's not as easy as A and B. It's a expression, but that's still a number. So this number is divisible by 3, which means I can factor 3 out from here. That's what I did. 2 to the 2k minus 1. You should be able to factor 3 from there times some integer. Although we don't see how, because they tell us, the problem tells us, the assumption tells us this is true. If they tell you this number is divisible by 3, 3 goes in there, you should be able to somehow factor out the 3 from there. That's the definition of divisibility. Okay, make sense? All right, again, number theory, you will have to do this kind of proof. Use the divisibility, the definition of divisibility a lot. Okay, so try to memorize the definition of that. Sometimes you don't have to put it there at this point because this is not our first class anymore. You don't. I just assume if you put it there, I assume you know that you're using the definition of divisibility. So that's why I didn't put it there last time. But it looks like a lot of us don't remember that. Maybe you should write it down. That's by the definition of divisibility. Okay, if 3 divides that, you should be able to factor 3 out of there times the integer. And the next step, add 1 to both sides. That's algebra. But why did you do that? Does anyone remember why did we add 1 to both sides of that equation? Because we want to get 2 to the 2k by itself. And why do we want to get 2 to the 2k by itself? Because looking at the one we want to prove, so go back to this. This is the one we want to prove, 2 to the 2k plus 1. I'm going to go ahead and put them right next to each other so you can see better. So one of them, the one in the assumption is 2 to the 2k minus 1. The other one is 2 to the 2 times k plus 1 when we're replacing this k with the k plus 1. And what we need to do is to try to figure out, well, somehow there must be a connection between them. Well, mainly it's these two here. What is the connection between them? Well, how do we get one of them from the other, in other words? So we can look at these two. So minus 1 is already the same, so we don't need to worry too much about them. So these are the two ones we need to compare. First of all, you can distribute the 2 to get 2k plus 2. You can see better. Okay, so now look at them. How do we get one of them from the other? Well, I can put this question here. 2 to the 2k times what is equal to 2 to the 2k plus 2?
2.
2? Is that 2, Curtis? If
Yeah.
it's 2, what's the exponent of 2?
1.
So by using the formula, what will you get? 2 to the 2k plus 1, but we need a plus 2 there.
Oh, yeah. So it would be
So
4.
we should, or just put 2 to the second power, right? Is that
Yeah.
right? Okay. So this is an algebra formula that I didn't go over at the beginning of the class, and because that's something you have to know in order to do this continued proof. Okay, so go back to the question here. What is the statement we need to prove? The one we need to prove is right here. Okay, 2 to the, this one can be pretty much simplified as 2 to the 2k plus 2 minus 1. We want to show 2 to the 2k plus 2 minus 1 is divisible by 3. which means you have to be somehow able to factor a 3 out of this expression. When you look at this, you cannot factor 3 out, but we can use something we already have, and we already know. So we start with this left-hand side, so it's 2 to the 2k plus 2 minus 1. And again, because 2 to the 2k plus 2 is equal to 2 to the 2k times 2 squared. That's what Curtis said, and also James. So we're clear how I got this? So I just split 2k plus 2 as 2k and the 2 exponents. The formula we used from algebra is if you have, like say, x to the nth plus x to the nth, which is going to be equal to x to the m times x to the n. In algebra class, most of the time you're given this and ask you to add exponents, right? But in this class, you also need to know if you are given exponent of m plus n, you can rewrite it as the product of these 2 exponents. So that's why we did it, doing backwards of that formula. And look, there's a 2 to the 2k now. We can do substitution, right? Okay. So that's why we have to, in the equation we have, why did we add a 2 to both sides, add 1 to both sides? So we can get 2 to the 2k by itself, which gives us 2 to the 2k equals 3m plus 1, and replace that. So this will be replaced by 3m plus 1. Do it one more time here. So continuing this part, which gives us 3m plus 1 times 2 squared. 2 squared, now we can simplify it to get a 4 in there. So 2 squared is 4. And there's a minus 1. So that part in green is substitution. Where does this come from? It comes from the definition of divisibility. Since we know 2 to the 2k is divisible by 3, that means 2 to the 2k minus 1 is equal to 3 times some integer. After we add 1 to both sides by doing algebra, and we can get 2 to the 2k by itself, which is 3m plus 1. Okay, now, we got a much better expression now. Looking at the original one, this is the original one. There's no way we can factor out 3. But look at this one. We already see a 3 here. So that, but there's the minus 1, but we can, simplify this expression, combining like terms. Look, now, this expression is much better than that. See, when you look at this expression, no way you can factor out 3. But look at this one. We can see very clearly there is a 3 in there. So, what is that? This is the same as 3 times 4m plus 1, which means 3 divides that. So therefore, 3 divides 2 to the 2k plus 2 minus 1. Okay, now, that is proved. In other words, it's saying 2 to the 2k plus 2 minus 1 is divisible by 3. Okay, so that's the example I went over last time. Because it is, the algebra part is a little difficult. It's something we don't do every day. It's something probably don't do it in algebra class. So I try to go over this example one more time. The next type of question we're going to prove is inequality. So like I said, there will be 3 types of problems we're going to do using mathematical induction. One is like this kind of formulas type. Second type is divisibility. The third type, there's another one here. Number 6 and number 8 is pretty much the same. I think I might get rid of number 6 and just ask you to do number 8, because number 6 is asking you to write down the steps, what you should do first and second and third and fourth. But at this point, I think everybody knows the steps, so you may not need to do number 6, you just do number 8. So the third type of question we use mathematical induction to do is inequality. Look, there's a less than or equal to sign there. So this, I'm going to do an example similar to that. The one I'm going to do is on page 231. We want to prove for all integers n greater than or equal to 3. 2m plus 1 is less than 2 to the 2n. In algebra class, or maybe calculus class, we call this a linear function. When you draw the graph, it's a straight line. And the right side is an exponential function. It's like a curve. And graphically, you know, if in real life we do say that too, say, okay, the population is increasing exponentially. Whenever you hear people say something is increasing exponentially, it means what? Very quickly. Because it's much quicker than linearly or polynomially. So, yes, you probably know this from algebra class or calculus class that this number, exponential number, should be bigger than a polynomial number. But that's from the graphic point of view. But how do we prove it? Not just by looking at the graph, because when you're looking at the graph, it's not really a precise proof. And the graph, unless you make the graph, using the software to make the graph perfect, you may not get the exact answer. So what we do here is going to use the mathematical induction to prove this. Okay, so following the steps we did before. What should I do in my basis step? Substitute 3 for n. This time because they specify n equal greater than or equal to 3, so you're going to start with 3. And let's say because usually most of the question asks you to start with 1 or 0, right? Let's say if we start from 1, would this be true? Is this inequality true? If n is 1, what do we get? 2 plus 1, 3. 2 to the first is 2. 3 is less than 2. That's not even correct, right? That's why they ask you to start from 3. Because for the first few numbers, the polynomial number may be smaller than the exponential number. But when n is large enough, it should always be a polynomial number is bigger. So n equals 3. The left-hand side is equal to 2 times 3 plus 1. That's 7. Right-hand side is 2 to the third power, which is 8. Apparently, 7 is less than 8. And say left-hand side is less than the right-hand side. The basis case is proved. All right, do the inductive step. Okay, so the inductive step, you always start with what? Inductive step. You always start with the assumption. Assume what? What do we assume in this case here? This, whatever that is, it could be a formula, inequality, equation, inequality, or even a statement. Whatever that property is, you assume that statement is true for n equal to k, right? But in this case, what will this? We got an inequality. So what will this inequality be if n equals k? Catherine.
2k plus 1 is less than 2 to the k.
Yes, good, very good. Okay, so this is the one we assume to be true. So remember, you don't need to prove this one. When you say assume this is true, which means you already know this is true, okay? But what do we need to prove? So that's something you're going to put on your scratch paper or, leave a little bit of space to write it somewhere. So what do we need to prove? We need to assume that inequality, the property is true for n equal to k. We always prove whatever that statement is for n equal to k plus 1, right? So this comes from n equal to k. So we want to prove this is true for n equal to k plus 1. Elena, do you know what the inequality will become when n equal to k plus 1?
2k plus 1.
2 times k plus 1. Put a parenthesis for that, okay?
Plus k plus 1.
Plus 1. Okay? So replace this letter n with k plus 1. Continue.
Because I had a
Whatever this is, so this is inequality, right? So all you have to do is to replace the letter n with k plus 1. So what do we get?
on the other side down, right? Where it's
2k plus
2 to the less than 2 to the k plus 1. Yes. Okay. So in the inductive step, you look at what the inequality they give you. So this is the one we need to prove. And we replace n with k and replace n with k plus 1. I did mention this one time in class. I said, if you don't want to replace n with k, you want to use n, keep n and n plus 1, that's fine. At some point, you will be able to understand this. But sometimes you get confused. How can we replace n with n plus 1? If you get confused, always use k, different letter. Okay, I do notice, I think, Danielle, you use the n and n plus 1, right, in your homework. I mean, that is fine. If you don't want to change the letter to a different letter, you can. But again, it would make, if it's confusing, you can always use k and k plus 1. Okay, so we replace the n with k. We got this inequality. We replace the n with k plus 1. We got another inequality. So this is one. The top one is the one given, the known. The assumption is the one we know. This is the one we don't know. Put a question mark here. So we want to prove this one right here. Okay. We proved the equation before. We also proved divisibility. But when you really look at divisibility, it's pretty much still like equation. Because how do you prove divisibility? By the definition, you still have to write it in like an equation, an integer times 3. This one is different. It's an inequality. Okay, so take a look. How do I prove this from that? You can still use substitution or use the properties of inequalities. Okay, so any idea what we should do? If 2k plus 1 is less than 2 to the k, how do you prove 2 times k plus 1 is less than 2 to the k plus 1? Any idea? You don't have to tell me exactly. You just have to say something like, we can do this, and we can start with this or that. Multiply both sides by 2. Okay, that's one way you can do. Yes, that will work. So what James said, you could multiply both sides of this equation by 2. There are different ways you could do it. Maybe I'll show you a few different ways. There are at least 3 different ways you could do, maybe more. You can pick the way you like. So what James said is, I'm going to start with this and multiply both sides by 2. And can you see why he does that? And James, why do you do that? Do you know? Yes, that's right. Because the reason he did that is he's trying to match the right-hand side. Okay. A lot of times we try to match the left-hand side, which will still work in this case. I'll show you a different way. Try to match the left-hand side. So what he did, he saw, okay, that's the formula you just went over, 2 to the 2k and 2 to the k plus 1. I can take 2 to the k times 2. That would give me 2 to the k plus 1, right? So that's why he decided to multiply both sides by 2. Because when you multiply 2 to the k and the 2, that would give you 2 to the k plus 1. So first of all, you're going to get the right-hand side to match. Well, that will work. What is the other way? What if I say I want to match the left-hand side? What should I do? Or if I want to do substitution, what should I do? If you want to match the left-hand side, you look at them. What is the connection between them? Well, how do you get this from that? Usually you start from this easy one, simple one, 2k plus 1. Try to get the complicated one. How do you see the connections between these two? Can you?
The bottom is 4 or more. You just need to add 4 to it. Or wait, add 4 to the top.
Add a 4 to the top. 4? Why is that 4?
Just because after you distribute the bottom.
Yes, that's right. That's what I like to hear. Yes, okay. Distribute that 2. That would give you 2k plus 2 plus another 1. What would that be?
3
2 times k, it would be 3, right? Or let me just leave it. How about let me just leave it? So when Curtis, if you distribute 2, then you will get a 2k plus 2 plus 1. And what's the number we should add?
2.
2, yes, that's right. So you can add 2 to both sides. That's the other way. Or you could do, I know, was it last Wednesday when we started talking about mathematical induction, Curtis said substitution, right? For this case, you can still do substitution if you want, okay? Instead of adding 2 to both sides, you could put 2k and plus 1 together. 2k plus 1 is less than what? 2 to the 2k, right? So when you see 2k plus 1, that's smaller than 2 to the k, sorry. Okay, so there are many different ways you can do. I'm going to show you maybe 3 different ways, and you can pick the way you like. Maybe I'm going to start with this way, the way Curtis said, and then I will talk about James, the way James said it later. So we noticed after we distributed, so usually when you get a question, even if you don't know where to start, when you see a parenthesis, you probably should multiply out, see if you can make connections between that. So after we multiply them out, 2k plus 1, 2k plus 2 plus 1, apparently there's a plus 2 there. So we can add a 2 to both sides. Now, that's something you should have learned in algebra. Go back to algebra question. What if you have, let's say, 3k minus 2 less than 6. How would you get x by itself? What would you do to get k by itself? You would add a 2 to both sides. That would still keep a less than sign, right? So that is something we did here, sort of similar, but for a different reason. Over here, because we want to get rid of negative 2, that's why we added 2 to both sides. Over here, the reason is we want to match the left-hand side. That's why we decided to add a 2. But it's a property in algebra for inequality. When you add the same number to both sides of the inequality, this inequality sign will not change, so you can still get a less than. On the left-hand side, we got exactly what we needed, 2k plus 2 plus 1. On the right-hand side, we've got 2 to the k plus 2. And that is something different. Well, right here is different. Even what I just talked about before is trying to match the left-hand side. That is the same thing we did before with equations. Take a look at the one we have so far. Okay, so these two match. They match now, but they don't match. What I need is to prove 2k plus 2 plus 1 less than 2 to the k plus 1 in the exponent. What we have is 2 to the k plus 2, and this plus 2 is not in the exponent. Can we show they match? That's why we did it with the equations, right? We always say, okay, they're different, but we equal denominators, add them, and factory, we should get them to match. But for inequalities, most of the time, I would say probably 100% most of the time, or maybe there's 1% chance, but they are not going to match. Because we're trying to prove a number is less than a number. We're not trying to prove they are equal. And you don't have to show that they are equal. So here, can anybody see what our next approach should be? What would be the next step? So we want to show 2k plus 2 plus 1 is less than this number. But what we know is 2k plus 2 plus 1 is less than a different number. So what if you show, what do we need to prove here in order to get what we need to prove? It suffices to show what's left to do. There's only one thing left, one step left. Does anybody know?
No.
Huh?
No.
No? Okay. All right, let's start with something very basic in algebra. If I have, let's say, three numbers, so if I tell you if A is less than B, and you can add a condition and something, then A is less than C. What should the condition that I add here? It will make this statement true. wait, B is, what did you say again, James? B and C is greater than, wait, C, what, say, did you say C is greater than B, or C is greater than B, or in the other words, what, B is what? C is greater than B, which means B is less than C, right? Yes, that would be correct. Can you all see this? When you have three numbers, if the first number is less than the second, and the second is less than the third, you can conclude what? The first must be smaller than the third. Make sense? That's sort of like a common sense, right? Okay, say in real life we have this kind of, later at the end of the semester we will talk about this. This is called a transitivity. It's a transitive property. So whenever you have three people, three numbers, say if A is younger than B, B is younger than C, you can conclude what? A must be younger than C, right? Okay, the same thing here. If a number A is less than B, and B is less than C, you know for sure A is less than C. So if you want to prove A is less than C, but what you know is A is less than different number B, all it's left to prove is what? B is less than C. If you can prove B is less than C, then you're done, you're finished. A must be less than C, right? Make sense? Okay, so go back to where we got stuck. See if you can figure out now what we should do. So this is like the number A. What do we know? We know A is less than B. A is less than B. We want to prove that's A. A is less than C. So if we can prove what?
B is less than C.
Yes, so you need to prove this is our B and this is our C, sort of like a C. So this is our A and A here. So we know A is less than B, and we want to prove A is less than C. So this property that I just went over tells us, okay, if you can prove this, then you're done, okay? So I need to prove B, this number B is less than that number C, which means you got to show 2 to the k plus 2 is less than 2 to the k plus 1. That's the only thing left. How do we do that? Again, it involves algebra. I'm going to write on a different paper, but you can add it here later. So first I'm going to ask you to compare them. This is what we need to prove. D is less than C. So if I can show 2 to the k plus 2 is smaller than 2 to the k plus 1, of course, the A is going to be smaller than C now. But the question is why? Why is this number smaller than that number? Okay, so now they look different. So maybe you should try to get them as close as possible so you can compare. Take a look at the right-hand side. So I'm going to start from the right-hand side. You can start from, later when we really write down the problem, you might need to start from the left-hand side. But when you are thinking how to prove this, you actually start from the right-hand side. So we're going to start with this and to make changes to that so you can get close to the expression on the left-hand side. So what changes can we do? What algebra work can we do here to this exponent? 2 to the k, right? That's what we just used before, right? Okay, exactly the same as the one we did before. 2 to the 2k plus 2 is equal to 2 to the k times 2 squared, right? So the same formula we're using. Okay, now it's getting a little bit closer, 2 to the k, 2 to the k. But instead of having a plus 2, I have a times 2. In the past, we did have students who say, well, when you multiply a number by 2, it's going to definitely be bigger than adding 2 to the same number, which makes sense. But if you want to explain more, if someone asks you why, okay, I think most of us will agree, okay, when you double a number, it's going to be bigger than adding 2 to a number, right? Most of the time it's true, okay. Although it seems obvious, well, if someone says, I don't understand why, and then you still have to prove it. So how do you prove a number times 2 is going to be bigger than a number plus 2, or a number adding 2 to a number is going to be still smaller than the number times 2. And on Monday, I did give you a problem to do. If you see if you still remember this question. What's 2 to the k plus 2 to the k? Anybody remember? 2 times 2 to the k. Good. Is that right? Why? Because it's just like x plus x. What's x plus x? It's 2x, right? Instead of having an x, what I have is 2 to the k. But 2 to the k is still a number. It can be considered as a variable. So if you remember that, that's what we're going to use here. So when I go back to this, what does 2 times 2 to the k mean? I can change multiplication to addition so I can get close to that on the left-hand side. So this is what I do. 2 to the k times 2 equals what plus what? Yes, very good. So it's equal to adding 2 copies of 2 to the k. That's, again, algebra. Okay? Make sense? Just like if I give you x times 2, you can write it at what plus what? What plus what is x times 2? X plus x, right? The same thing. So if I give you 2 to the k times 2, it's 2 to the k plus 2 to the k. So that is from more like the definition of multiplication. Now take a look at the right-hand side, the modified form. Originally, that's what we had. But now, after using algebra formula of definitions, I got 2 to the k plus 2 to the k. It's much easier to compare this one with the original left-hand side. So this is the new right-hand side. Now compare them. The left-hand side is 2 to the k plus 2. This is the left-hand side. The right-hand side, instead of using this one, I'm going to use the changed one, 2 to the k plus 2 to the k. Can you compare these two? See which one is... Can you see why? Or we already know we need to show that is smaller than that. Can you explain why this is smaller than the right-hand side? Y is 2 to the k plus 2. Smaller than 2 to the k plus 2 to the k. Is that obvious?
Is it because k can't be less than 3?
Right, yes. So even if k is equal to 1, let's compare these two numbers. Because 2 to the k and 2 to the k, they're the same thing. The only difference is this number and that number, 2 and 2 to the k. When you compare these two, can you tell which one is bigger, which one is smaller? 2 is definitely what? Smaller than 2 to the k, right? Because what Curtis said, that this exponent k in the problem, it was specified that exponent should be greater than or equal to 3. In fact, if k is greater than or equal to 1, it will work. 2. And when you take a look, it's apparently true because if k is 3, you got an 8. 2 to the third, that's 8. 2 is smaller than 8. If k is 4, you got a 16. If k is 5, you got 32, 64. So that number on the right-hand side is just going to be bigger and bigger and bigger when the k changes. Doesn't matter what k it takes. It's always going to be bigger than 2, right? So let's go back to these two numbers again. 2 to the k plus 2 and 2 to the k plus 2 to the k. Because the number circled, 2 is always smaller than 2 to the k. When you add the same number 2 to the k, of course, it's still going to be smaller, right? Is that right? Okay, so when you have 2 is smaller than 2 to the k, if you add 2 to the k to both sides, add 2 to the k to the left, add 2 to the k to the right, you're going to get 2 to the k plus 2. Use rule for the original right. It's still going to be less than 2 to the k plus 2 to the k. That's the property of inequality. If something is less than another, adding the same number will not change the inequality sign. Okay, so that's proved, right? But when I go back to write down the proof, you have to put the way that, assuming nobody understands how to prove this, you have to put write the ways so other people can understand what you're doing. So this is the way usually I do. I'm going to reversing what I did. If you notice that I said, okay, I'm just start from the right-hand side because I noticed that this is 2 to the k times 2 and then 2 to the k plus 2 to the k. And then I found out 2 is always smaller than that. But when I do the problem, I'm going to go backwards. I'm going to start from the left-hand side. Start with this. And this one, I know it's going to be less than 2 to the k plus 2 to the k. Is that right? That's what we just explained. Can everybody understand why 2 to the k plus 2 is smaller than 2 to the k plus 2 to the k?
Yeah.
Yes, because 2 to the k is a much bigger number than 2, right? So when you add a bigger number than 2, of course, it's going to get bigger. So that's why adding 2 to the k is going to be smaller than adding 2 to the k to 2 to the k. Okay, so that's from algebra. You don't have to explain that. Just if you do want to explain, if someone asks you, you can say because 2 is less than 2 to the k. Adding a bigger number will make it bigger. I think that if you don't put any explanation there, that's fine. Now, by algebra, what is 2 to the k plus 2 to the k? That's the question I just asked you at the beginning. What's 2 to the k plus 2 to the k?
2k plus 1.
Hey, what? Say it again.
2 to the 2k plus 1.
Oh, you skipped a step.
Oh, like
How did you know?
just the next one? It's
It's
2 times 2 to the k.
Times. Yes, that's right. We don't really have a formula for 2 to the k plus 2 to the k. You can get 2 to the k plus 1 immediately. I'm sorry. There's not a plus 1 there. Okay, so it's just going to be 2 times 2 to the k. Why? Because, again, algebra. X plus x will give you 2x. 2k plus 2k will give you 2 of that. 2 times 2 to the k. And the next part is the formula, adding exponents. 2 times 2 to the k will be 2 to the k plus 1. Right. So this is this part of 2 to the k plus 1 right there. So we're done. We proved, what did we prove? We proved that this number, a, 2k plus 2 plus 1, is less than 2 to the k plus 1. Because, well, it's smaller than 2 to the k plus 2, but 2 to the k plus 2 is also smaller than 2 to the k plus 1. Of course, it makes the first number smaller than the last number. Maybe I can, if this is a little messy, I can rewrite this part for you so you can see better. So this is the way I did. Let me just go ahead and copy this. So in the inductive step, you always assume the formula is true. So we assume 2k plus 1 is less than 2 to the k. And adding 2 to both sides. Well, so looks like I know what to do, adding 2 to both sides. But in fact, if someone asks you, how did you know you should add 2 to both sides? Well, because we did something at the beginning on the scratch paper that we multiplied out and noticed that we need to add a 2 to both sides. So we added 2 to both sides to get 2 to the k plus 2 plus 1, less than 2 to the k plus 2. And 2 to the k plus 2, this 2 is an exponent, continue right here, is equal to, maybe let me write down one more step and copy everything. 2 to the k times plus 2 plus 1 is less than 2 to the k plus, times 2. Oh, that's not an exponent, sorry. Plus 2 to the k. And copy the next step, 2 to the k plus 2 plus 1. If you don't want to write the left-hand side many times, you can just do the right-hand side. 2 to the k times 2, which is equal to 2 to the k plus 1. And the left-hand side, you can leave it this way if you want to, or you can factor out of that 2 so you can match the formula we have. And now we proved that 2 times k plus 1 is smaller than 2 to the k plus 1, which is what Alina asked Elena to say at the very beginning. So that was the one we had at the very beginning. 2 times k plus 1 less than 2 to the k plus 1. All right, so that's how we prove inequality. Like I said, there are different ways, so maybe I can do a different way. Let's see. if we do substitution, okay, so if we do substitution, I'm trying to think about substitution, see if it will still work. So if we do substitution, solution 2, for the induction step, you start with to the left-hand side of the equation, the inequality that we want to prove. But this is something you always have to write it down. You can put it on a scratch paper if you don't want to put it on the paper, because that's your goal. That's what you want to prove. You can start from the left-hand side, 2 times k plus 1 plus 1. This is equal to 2 to the k plus 2 plus 1. And I can switch 1 and 2 to put a 2 to the k plus 1 together and the 2 separate. Why? Because I want to use the assumption. The assumption says 2k plus 1 is smaller than 2k. So that number is smaller than 2 to the k. When you do substitution, you do have to be careful, because are these two numbers equal to each other? No, they're not equal. So you cannot keep the equal sign anymore. We have to put it less than, because it tells us in assumption 2k plus 1 is smaller than 2 to the k. So when you replace 2 to the k plus 1 with 2 to the k, you also have to change that equal sign to less than. So that's sort of like a substitution we did, replacing 2k plus 1 with 2 to the k. But you also have to change the equal sign to a less than sign. Okay, when you get here, you do the same thing pretty much we did before. Because 2 is less than 2 to the k. So when you add a bigger number to 2 to the k, it's going to get bigger. So that's why we keep the less than sign. And next part is equal sign, because 2 to the k plus 2 to the k is equal to 2 to the k plus 2, which is also equal to 2 to the k plus 1. So combining, that's the other way to write a proof. Sort of like using substitution. The left-hand side and the right-hand side we need. The whole thing. This is equal to this, smaller than this, smaller than this, equal to this, equal to that, which means that has to be smaller than this. Solution 2. Solution 3 is what Jane said. It's a different approach. So solution 2 and 1, although I did substitution in solution 2, it's still pretty much the same as solution 1. But solution 3 is what James said, trying to match the right-hand side, which will be a little different. So this is the one we start with, 2k plus 1 less than 2 to the k. Now, James said we can multiply both sides by 2. In that way, I can get 2 to the k plus 1 immediately. Let's try to do that and see what happens. So multiply the left-hand side by 2, multiply the right-hand side by 2. So we're going to get 4k plus 2 less than 2 to the k plus 1. Well, what do we need to prove? That's not the one we want to prove. The one we want to prove is right here. 2 times k plus 1 plus 1, which we simplified as right here, 2k plus 2 plus 1. You will combine it as 2k plus 3. So the one we want to prove is 2k plus 3 less than 2 to the k plus 1. After simply distribution and combining like terms, the left side should be 2k plus 3. Previously, I left it as plus 2 plus 1 because I can compare it to that. There's a plus 1 on the left-hand side. That's why I didn't combine them. Over here, there's it's easier if we combine it. So this is the one I want to prove. The right side match, the left side don't match. Previously, we matched the left-hand side. Left-hand side match, the right-hand side don't match. These two numbers don't match. We did some work to show that B is smaller than C. Well, take a look at this one. What do you think we should prove? We want to prove, we call this number A, call this number B, call this number C, and that is still the same B. So we want to show number C is smaller than B, but we know A is less than B. What do you think we should need to prove in order to show C is less than B? Yes, so C is smaller than A, right? If this number is smaller than that number, C is less than A. We already know A is less than B. What conclusion can you get? C is less than B, right? Make sense? So we already know A is less than B. If you can prove C is less than A, C is smaller than A less than B, that will give you the conclusion C is smaller than B, which is what needed. So in his case, he will have to show this number 2k plus 3 is smaller than 4k plus 2. How do we do that? Or you can say 4k plus 2 is greater than that. So let's look at the algebra work here. So you are going to take, we want to show 2k plus 3, the C, smaller than 4k plus 2. Why is this true? You can solve for k, see if it works. That's one way. You can subtract the 2k from both sides. 3 less than 2k plus 2. And subtract 2 from both sides. You're going to get 1 is less than 2k. Okay. And is 1 less than 2k? Always, right? For any k, it's actually k starts from 3. If k is 3, 2 times 3, smallest 2k will be 6. If k is 4, you get an 8. If k is 5, you get a 10. So this part is definitely going to be bigger than 1, right? So when you look at them, you may not be able to tell why 2k plus 3 is less than 4k plus 2. But after you simplify, you can see better. If 1 is less than 2k, yes, then 2k plus 3 is going to be less than 4k plus 2. So the way I am going to write is going from the bottom to the top. So I'm going to start with this. 1 is less than 2k. I'm just going to copy it. So I'll say since 1 is less than 2k, instead of subtracting 2, I'm going to add a 2 to both sides. 3 is less than 2k plus 2. Adding 2 to both sides. And then I will need to go back. So I subtracted 2k from both sides, right? Then we're going to add a 2k to both sides. So add a 2k to both sides, 3 plus 2k. Or maybe 2k plus 3 is going to be less than 4k plus 2. And we're done because... So my thinking part is I start with the inequality, trying to go back to see if I can get a contradiction. Assume this to be true. I did not get a contradiction. This is true. If this is true, means 3 less than 2k plus 2 is true, which also means the original is true. But when I write down the proof, I should start from the bottom and reversing the operations. Subtracting 2, you add 2k. But if you say, well, this confuses me, I don't like this way. If you don't like this way, you say, okay, from that to that, I understand. But when you reverse it, it's confusing. Then you can do that way, but you just have to use something. When you write it, to make it this way. So when you write it, this is how you write it for that part right there. So like I said, I reversed everything. But if you don't like that, so how do we prove? So how do we prove 2k plus 3 is less than 4k plus 2? You can put if and only symbol. So 2k plus 3 is less than 4k plus 2. If and only if the next operation is true. After you subtract the 2k from both sides. 3 is less than 2k plus 2. And when would this be true? Again, notice how you got this. You subtract 2k from both sides, from algebra. And then you subtract the 2 from both sides. That's when would this be true? If and only if 1 is less than 2k. Well, because 1 is less than 2k. That means 3 is less than 2k plus 2. That means 2k plus 3 is less than 4k plus 2. So if you want to do it the way we do in algebra, put equivalent signs for them. So you can do this way, okay? But usually we don't want to start the proof with this because it's kind of what I didn't put it. Say it's kind of like saying, in order to prove 2k plus 3 is less than 4k plus 2, we need to prove 3 is less than 2k plus 2. In order to prove 3 is less than 2k plus 2, then we need to prove 1 is less than 2k, which because this is true, that is true, that is true. But just don't do the way I did at the beginning. Say, okay, start with this and go all the way down, okay? So if you want to do this way, put equivalent signs. Okay, so that is 3 different ways to do, to prove inequality by mathematical induction. Questions? Well, I don't know which way you like better. Trying to either match the left-hand side or match the right-hand side. So when you do any question, you have those 2 options. Usually, I always try to match the left-hand side. But if you want to match the right-hand side, that can also work. Okay. All right. So now, so no questions? Well, we still have about, I guess, 15 minutes, a little less than 15 minutes. We can move on to 5.1. So we're going to skip 4.4. It's a stronger version of mathematical induction, which we will skip. Look at chapter 5. Set theory. Okay, 5.1, basic definitions of set theory. In 5.1, you have to memorize a lot of definitions. There are no proof questions for 5.1, but it's just many definitions that you have to memorize. So we're going to start with the set notation. I think you know that from algebra class. Set notation looks like that, right? Okay. 2 curly brackets. What we have, you can put anything in there. A list of numbers, a list of people, but you can also do a description. Sometimes you may not be able to list everybody. Then you will have to describe it. So, for example, you could do x is greater than or equal to 1. Because you cannot, if x is a real number, so let's mark a real number here. So if x is a real number, you cannot list all the real numbers. It's not just going to be 1, 2, 3, 4, 5 because you are missing 1.1, 1.11, 1.123, 1.11 something. So there's no way we could list. If you cannot list anything, you can describe it. X is a number greater than or equal to 1, and it's also a real number. Unless you know x is an integer. If you know x is an integer, you could list like 1, 2, 3, 4. That's for integers. Okay. Next, we're going to look at. You mean if you can use set notation for prime numbers? You can do both ways. So you can list. See, when you list them, well, there is a possibility that some people will not get what you're trying to do. So they may not realize you're listing all the prime numbers. But I think most of the people, when you can list a few more, 11 and 13, I think after first few numbers, they will say, oh, okay, looks like they're all prime numbers. But maybe some students, they won't, or some people just don't know what numbers they're trying to list, okay? So probably you can do this different way. Just say, okay, all prime numbers. And just put them in there. Just give a description. Or you can put x. X is a prime number. So sometimes you could do both. You could list it, or you could give a description, or whatever way you like, whichever way you think is easier. But in some cases, you cannot list them, like this case. If X is a real number, you cannot list all of them. You just have to describe it. Okay. I did talk about all these set notation before when we talk about one of the sections was, I forgot which one. I think it was in the chapter 2, universal quantifiers maybe. We have some symbols to represent certain number of the set of certain numbers. R to represent what? A set of what? Real numbers, right? And we have, what about the integers? What's this letter we use?
Z.
Z, yes. We use the Z. What about a set of rational numbers?
R,
the fraction. Huh?
Oh wait.
Fractions. We use Q. Because fractions is what, like a quotient, right? Okay. So Q sort of like represents quotient. Anything else? We have Z, integers. We have whole number for using W instead of whole numbers. And you can also use things like R plus. What does the R plus mean? Positive, yes. The set of positive real numbers. A Z plus means the set of positive integers. Or Q plus means the set of positive rational numbers. W you don't have to. I guess you can still do it because W includes 0. What about the set of natural numbers, which does not include a 0? You take a letter. You can take the letter N, capital letter N. Okay. I think that's all the symbols we're gonna have. Next, we're gonna introduce a concept called a subset. Okay. So we know what a set is. We learned that, we see that in algebra class. Have you all heard of a subset? So what is a subset? Subset is also a set. The definition, well, like I said, most of the time previously, when I give you a definition, what's a statement? Well, what is a quantifier statement? What is a conditional statement? I did write them down, but I always said, okay, you don't have to memorize those definitions as long as when you see a statement, you know what it is, right? But for most of the definitions here, you do have to memorize them. Because when you do the proofs, when you do the even not proof questions, like the calculation problems, or not really calculation, operations, section operations, you do need to know the definition. So what's the definition of subset? When we have a set A and a set B, so this is how we define it. We say a set A is a subset of set B if and only if. All the definitions are if and only if. If and only if every element of A is an element of B, of A, is an element of B. Element, when we say element, there are other ways to say element. You can call it a member. Every member of A is also a member of B. Element or member are the numbers inside. Well, not necessarily number, could be people. So for example, 2 is an element of this set. 3 is an element of this set. Even the one we listed before. So if I ask you, is 3.5 an element of the set? Yes, right? Okay. Because 3.5 is greater than there. So we say 3.5 is an element of the set. Instead of saying this set, that set, we usually use capital letters to represent a set. If I call this a set A, then I can say 3.5 is an element of A. Be easier. And have we talked about belong to the symbol. Have we talked about the other way to write this is 3.5 belongs to A? Have we seen the symbol? Yes, we have. Okay. So when you say is an element, that's a lot of words, right? So we can use a very easy symbol. Well, kind of like E, but it's not really E. It's round. So belong. It's like saying an element, what belong to. Okay, so go back to that definition of subset. Every element of A is an element of B. So that's a sentence. Now, I can use symbols to rewrite the sentence. A lot of times when you write down the proof, you can use symbols. So this is what I use symbols. So what does this mean? It means for any element A, I'm going to use X to represent element A. X is also in B. So that whole sentence can be described in a very short symbolic form. So we did talk about universal statement. So this is how we use it, and you can write it. This is fine. In even a published paper, you could use the symbol because that's a symbol we all use in the proofs. So let's read this. It seems like a little different from that. It says for any. Remember the symbol means for any or every, or any, or you can say it's every. How do we read this? X belongs to A. So for any element X in A, you can also read it like in A, X is also in B. So, or for any element X of A, X is also element of B. So that's, when we write down the proofs, we are going to take this way of writing, using symbols. We don't really want to use sentences all the time. But you need to know what it means. So when you write down the proof, and when you write this down, you should know, okay, I'm trying to prove if X is an element of A, then X is an element of B. That will help you. Translating to English sentences will help you do the proof. So let me give you an example. Two sets here. Example to show subset. What's a subset? If we have a set A that has elements, say, 1, 2, 3, and B has elements of 1, 2, 3, 5, and C has elements of 2, 3, and 4. Okay, now look. Can you find any subsets of another? And C? Okay. A is a subset of B, but not a subset of C. Right? It's a little tricky here because I don't have 1 there, right? So A is a subset of B. By the definition, how did you know A is a subset of B? Yes, this is what you check. You take element by the definition. The definition of subset means every element of A is also element of B. So I checked, okay, the first element is an element of B. Second element of A is an element of B. Third element of A is an element of B. So that's when you say, okay, A is an element of B. Okay. But A is not an element of C because, we found out the first element, 1, is not an element of C. It's not in there, right? What about a C and B? Is C a subset of B? Well, 2 is in there, 3 is in there, but 4 is not in there, so, which makes C not a subset of B either. Okay, we can stop here for today. By the way, the symbol we use for subset is this. Sorry, just one last note here. That's the symbol we use. It's, like this. We say A is a subset of B.
Your meeting has ended.